In this video, I want to discuss something called the principal unit normal vector. Now that we know how fast a curve turns, let's look at the direction of the turn. We need a vector that's going to be easy to work with and that will have the same direction as the derivative with respect to s of the unit tangent vector. This vector is what we call the principal unit normal vector. This is a unit vector that will have the same direction as the derivative with respect to s of the unit tangent vector. If we let vector r describe a smooth parametrized curve, the principal unit normal vector at a point P on the curve where my curvature kappa is not equal to 0 can be derived as follows. I will take kappa of s to be defined as 1 over the speed times the magnitude of the derivative with respect to s of the unit tangent vector. Then my principal unit normal vector, capital N of s, will be given by the derivative with respect to s of the tangent vector divided by the magnitude of the derivative of the tangent vector with respect to s. We can write this as 1 over kappa times the derivative of the unit tangent vector with respect to s. If I use the parameter t and the chain rule, I can get an alternative form of the principal unit normal vector. The principal unit normal vector, capital N of t, will be given by the first derivative with respect to t of the unit tangent vector over the magnitude of the first derivative with respect to t of the unit tangent vector, which can also be written as 1 over kappa times the derivative with respect to t of the unit tangent vector. Then I evaluate this using the value of t that happens to be associated with the point P on my curve. Now let's talk about the properties of the principal unit normal vector. I'll start with a vector r that describes a smooth parametrized curve and has a unit tangent vector of capital T and a principal unit normal vector of capital N. The vector capital T and the vector capital N are orthogonal to each other at all points of the curve. This means that the dot product of the unit tangent vector with the principal unit normal vector will give me 0 at all points where the principal unit normal vector is defined. The principal unit normal vector points to the inside of the curve. This is in the direction that the curve is turning. Let's work an example. I want to find the unit tangent vector and the principal unit normal vector for the parametrized curve described by r of t is equal to a vector with the components 4 sine t, 4 cosine t, and 10t. Then I want to verify that the magnitude of the unit tangent vector is equal to the magnitude of the principal unit normal vector, and that the dot product of the unit tangent vector with the principal unit normal vector gives me 0. My velocity is given by a vector with the components 4 cosine t, minus 4 sine t, and 10. The magnitude of the velocity, or the speed, is given by the square root of 16 cosine squared t plus 16 sine squared t plus 100. This gives me the square root of 116, or 2 times the square root of 29. My unit tangent vector is given by 1 over square root of 29 times a vector with the components 2 cosine t minus 2 sine t and 5. The magnitude of the unit tangent vector is given by the square root of 4 cosine squared t over 29 plus 4 sine squared t over 29 plus 25 over 29, and this is equal to 1. My principal unit normal vector is given by the first derivative with respect to t of the unit tangent vector over the magnitude of the first derivative with respect to t of the unit tangent vector. This gives me 1 over the square root of 29 times the components negative 2 sine t, negative 2 cosine t, and 0, all divided by 2 over square root of 29. This reduces to a vector with the components negative sine t, negative cosine t, and 0. The dot product of the unit tangent vector with the principal unit normal vector gives me 1 over the square root of 29 times the quantity negative 2 cosine t sine t plus 2 cosine t sine t plus 0. This is equal to 0. It shows that my unit tangent vector and my principal unit normal vector are in fact orthogonal. The magnitude of my principal unit normal vector is also 1, which is identically equal to the magnitude of the unit tangent vector. So now you get to try it. Pause the video and find the unit tangent vector and the principal unit normal vector for the parametrized curve described by the vector r of t is equal to the components t, the natural log of cosine t, and 3. Then verify that the magnitude of the unit tangent vector is equal to the magnitude of the principal unit normal vector, and that the dot product of the unit tangent vector and the principal unit normal vector is equal to 0. When you're ready, restart the video to check your understanding. I first have to find my unit tangent vector and my principal unit normal vector for the curve described by the vector r of t is equal to the components t, natural log of cosine t, and 3. My velocity, v of t, is given by the components 1, negative tangent t, and 0. The magnitude of the velocity is given by the square root of 1 plus tangent squared t. This reduces to the secant of t. The unit tangent vector is given by the velocity vector divided by the speed. This gives me a vector with the components cosine t, negative sine t, and 0. The magnitude of the unit tangent vector is 1. The principal unit normal vector is given by the derivative of the unit tangent vector with respect to t over the magnitude of the derivative of the unit tangent vector with respect to t. This gives me a vector with components negative sine t, negative cosine t, and 0, and this is all divided by 1, so I can write it simply as the component vector negative sine t, negative cosine t, and 0. The magnitude of the principal unit normal vector is 1, which is the same as the magnitude of the unit tangent vector. The dot product of the unit tangent vector with the principal unit normal vector is given by negative cosine t sine t plus cosine t sine t plus 0. This is equal to 0, showing me that the two vectors are in fact orthogonal. This is the introduction to working with the principal unit normal vector. Don't forget that it is always orthogonal to the unit tangent vector at all points on my curve. Be sure and let me know if you have any questions.